The Dounreay fast breeder reactor was built and equipped within 3.5 years of the work starting on the site. When the erection of the sphere forming the fast reactor containment building had reached equator level, work started on the construction of the reactor vault. Built from the center anchor and inner skirt, this was to be a bowl-shaped concrete structure 90 feet in diameter, 45 feet high, with walls 5 feet thick. At the top was to be constructed the vault roof, supported by tubular steel columns rising from the floor. Inside the vault was to be installed the reactor vessel, supported by steel girders. Surrounding the reactor would be the primary heat exchangers and the electromagnetic pumps. Finally, on completion of the sphere, a Goliath crane would be installed on the vault roof. By the winter of 1955, 6 months after work first started, the lower half of the sphere had been built. It was 135 feet in diameter with a catwalk bracing girder around the equator. The first stage in the construction of the vault was the erection of the steelwork. This was built on the inner skirt and center anchor so that the weight of the finished vault would be transmitted directly to the foundations and not taken by the sphere itself. For the next 3 months, concreting work went ahead, by which time the walls had nearly reached their full height of 45 feet. During this period, a gantry, supported at one end by a tower rising from the center of the vault, was used to maintain a continuous supply of concrete. It was fed to monoskips running on a circular track erected on staging above the shuttering. The walls were to be 5 feet thick as a biological shield against radiation hazards inside the sphere, and permanent steel shuttering was used in their construction. Following the usual practice, the concrete was poured in sections and each pour was thoroughly vibrated to ensure that it was uniformly compacted. Once the construction of the vault had started, work went on day and night. Careful organization maintained the steady flow of concrete from the mixers to the hopper so that the skips were never held up for supplies. The top slab or vault roof was to be 5 feet 6 inches thick, supported independently of the sides by 12 steel columns set in a 58-foot diameter circle directly above the supporting skirts, so that the load of the roof would be taken by the foundations. The structural steel for the roof was constructed in 12 sections. In the center was to be a hole stepped from 26 feet to 23 feet in diameter for the reactor vessel. At the top of the vertical columns, fish plates were fitted, to which were bolted the sections of the roof steelwork. Over 200 openings had to be left in the roof for equipment and fittings. To position the liners for these, wooden templates were laid on the steel reinforcing sections and lined up by theodolite. Plumb bobs dropped from the template above were used by the fitters below to line up the openings to the very close tolerance permitted. As soon as the liners had been set, they were welded to supporting struts on the steelwork. When this had been done to all the fittings, concrete pouring began. The roof was cast in 3 lifts and the concrete was poured from skips in draftboard pattern. The infilling sections were poured as soon as the adjacent panels had set. Here too, every pour of concrete was thoroughly vibrated. This was particularly necessary to ensure that there were no voids around any of the numerous liners in the roof. With the completion of the roof slab, the construction of the vault was now finished. Supported by the center anchor and outer skirt, its whole weight of 9,000 tons bore directly through these supports to the foundations, so that any stress to the sphere itself was eliminated. Work could now begin on building the upper half of the sphere, and a tower was erected on the vault roof as a temporary support for the plates. Inside the vault, the vast circular chamber was clean and ready for work to proceed. The first stage was to fit the lagging to protect the concrete from the operating temperatures that were anticipated. When the reactor is in operation, the temperature inside the vault will be above 200 degrees centigrade. The lagging consisted of some 1,200 metal-clad panels packed with mineral wool. Strips were fitted over the joins in the panels, and an air space left between the lagging and the concrete formed part of a closed-circuit air cooling system which would be fed from outside the vault. In the roof of the vault were set the liners for the 24 electromagnetic pumps to be installed as part of the primary heat exchanger circuit. As the vault was 36 feet high internally, a temporary floor 10 feet above the base was erected to assist in the installation of these pumps and other equipment. Each pump had to be lowered by crane through the top of the sphere down to the temporary floor, skidded across to its position, and then hoisted up. These pumps will circulate the coolant through the reactor and primary heat exchangers. Conventional methods of pumping were unsuitable, but as the coolant was a liquid metal, electromagnetic pumps could be used with the advantage of no moving parts and therefore no driving shafts which would require sealing. After fitting the pumps, the primary heat exchangers were next to be installed. At the manufacturer's works, these units had been produced to rigid standards. They were constructed of stainless steel, continuous loops of concentric tubing forming a tube within a tube. The inner tube was held concentrically by three-legged spiders machined from solid stainless steel. Each section of inner tube was made up in the shape of a hockey stick. This was then slid into the outer tube and the return bend placed in position. The inner tube carrying the radioactive primary coolant was 4 inches in diameter, and the outer tube for the secondary coolant was 6 inches. Sections of the tubes were butted together and welded by argon arc. Great care had to be taken to ensure that the internal bead was as smooth as possible. Every weld was X-rayed, and for the examination of joins in the concentric tubing, a special technique was evolved, the X-ray beam being angled to prevent the overlap of images of the outer and inner welds. In addition, each section was gas tested. After inspection, sections were assembled on frames to make up complete units and dispatched by road to the site. As with the pumps, the heat exchanger units were lowered into the sphere and down into the vault. Space within the vault was at a premium. Once the reactor vessel was in position, it would not be possible to insert any further components of any size. Erection planning was therefore a major operation. It was necessary to store for later use some 2,000 sections of pipework in the vault before the vessel was brought in. Later, the heat exchanger units would be hoisted up and slung into their final position a few feet below the vault roof, and the sections of pipework would be used to connect them with the electromagnetic pumps and the vessel. The heat exchangers had been lagged at the works except the middle section of the return bends, which were left clear for strapping to the lifting frame. After installation, the lagging was completed. At the contractor's works, the reactor vessel was under construction. It has been described as the most complicated stainless steel vessel ever produced in Britain and probably in the world. It consists of a double-walled outer vessel with a smaller inner skirt to contain the core of enriched fuel and the breeder blanket. Around the inner skirt will be the control rod mechanism. The tolerances called for in the fabrication of the vessel were quite outside normal practice, such as limits of 0.4% circularity and 0.2% alignment. The top of the vessel will be sealed by two plug shields, one within the other. The inner shield has a 2 foot 9 inch opening set eccentrically in the plug. Both shields are designed to rotate, and bearing pads are fitted to ride on rollers. At two levels around the outer vessel are placed the 24 stubs, to which the ingoing and outcoming liquid metal pipework from the primary heat exchangers will be connected. When the vessel was completed, its transportation from the Midlands to Dounreay presented a number of problems because of its size and weight. These difficulties were overcome by fabricating a special steelwork frame for the vessel, which was then carried by road from Wolverhampton to Middlesbrough. At the port of Middlesbrough, it was shipped to Wick, 30 miles from the Dounreay site. Here it was winched off the ship by the towing tractor onto the low loader for its run to Thurso. This part of the journey was comparatively easy. But the road from Thurso to Dounreay was more difficult, as the builders of Fors Bridge had not thought of such awkward loads, and the road surface had to be raised for the vessel to clear the parapet. On arrival at the site, the vessel was lagged and covered with galvanized mild steel sheeting. Inside the vault, the vessel's supporting columns had been erected. These formed a double circle rising from the vault floor and would be nitrogen cooled when the reactor was in operation. On the top of each of the inner supporting columns were two projecting dowels which would locate the vessel. When lagging was completed, the vessel, still in its cradle, was taken alongside the sphere and upended, ready for lifting. The crown plate of the sphere was lifted off and the vessel removed from its cradle, hoisted up, and then lowered slowly and carefully down into the sphere. To facilitate handling at the final stage, the vessel was re-slung from a temporary A-frame on the vault floor. This was the last lift of heavy equipment through the top of the sphere, and the crown plate was replaced and finally welded into position. Roller bearings were fitted around the vessel. Holes in the underside of the bearings would locate on the dowels. The vessel was then lowered to its final position with the roller bearings resting on the supporting columns. This arrangement allowed for the slight movement expected to take place due to thermal expansion when the reactor was in operation. Whilst work inside the sphere had been proceeding, so work outside had been going well. Adjacent to the sphere, the heat exchanger building had been erected and the secondary heat exchangers were being installed. The purpose of these secondary heat exchangers is to transfer the heat in the primary circuit to steam generating plant. By using two circuits in this way, only the primary heat exchangers, which are safely contained in the vault, have radioactive coolant passing through them. A secondary heat exchanger unit consists of 5 tubes bonded in copper laminations. The outer 4 tubes contain the sodium coolant from which the heat is transferred through the copper to the center water tube. This is to ensure that if a leak occurred, the sodium would not come in contact with the water. The first stage of manufacture was to wrap the stainless steel tubes with brazing foil. To prevent the foil uncurling, the ends were trimmed and fused to the tube in a small furnace. Copper laminations were used to enclose the 5 tubes of each element. And the tubes with the brazing foil around them were inserted into the laminated assembly. Each tube was then expanded to ensure a tight fit against the copper laminations. After the first pass, the outside diameter was checked and the correct size of expanding plug selected for the second pass. The unit was then removed from the assembly jig, inserted into a heating tube, and placed in a furnace to fuse the tubes to the copper laminations. The ends of the tubes were then cold bent and the elements coupled together in parallel by headers. When assembled in the secondary heat exchanger building, there were 12 separate units, each serving 2 primary heat exchangers. There were 10 parallel water steam circuits in each secondary unit, and each of the 10 units was made up of 13 elements, so there were over 1,500 in the whole building. The steam raising plant consisted of 12 boilers with the usual feed water pumps, circulating pumps and other ancillary equipment. The plant was designed to be a slave to the reactor, generating steam automatically in accordance with the reactor power output. The heat in the steam is rejected from the system either to dump condensers or to a turbo alternator. Inside the vault, the primary heat exchangers had been fitted in their final position, and above them the work of assembling the complex system of stainless steel pipework forming the heat exchanger circuit was taking place. This was a back-breaking task, due to the very confined space below the vault roof in which the men had to work. All the sections were of stainless steel and were welded by the argon gas process. There are over 3,000 such welds, and each was radiographed and gas tested to make absolutely certain that a perfect joint had been made. To maintain the sodium free from oxide contamination, cold exchanger circuits. The control of the fast reactor was typically groups of fuel elements, some 30% of the core. The raising and lowering of each group was to be accomplished by a control rod mechanism. The design and construction of this mechanism presented a number of problems. When in operation within the reactor, the up or down movement of the mechanism is controlled by electromagnetic clutches at the top. This also enables the reactor to be shut down quickly and safely, as any deliberate interruption of the electric supply would allow the control rods to fall rapidly out of the core. The control rod travels inside a carrier tube. To ensure smooth movement of the rod mechanism within this tube, roller bearings were fitted at necessary points. Each rod was tested on a rig at the works before dispatch. For insertion into the reactor, the hinged bottom arm of the mechanism had to be in line with the main shaft. A screw mechanism at the top, connected to the brace arm below, brought the bottom arm up to the horizontal, its permanent working position when in the reactor. Checks were then made to ensure that the horizontal arm would carry a load well in excess of that due to its group of fuel elements, and also that it would move smoothly in its guide tube. On delivery at Dounreay, the control rod mechanisms were inserted into their respective guides at the top of the reactor vessel. The complicated design of this mechanism was planned to permit the withdrawal of the control rods should it be necessary when the reactor was in operation. After final adjustments in the control rod chamber, the drive at the top was operated to bring the bottom arm up to its working position. When the reactor is in operation, the cup at the end of this arm will support one of the groups of core elements, and by lowering them out of the core, reactivity would be reduced or increased by raising them back into the core. By now, the airlock was the only access into the sphere. When the time came to erect the Goliath Crane, it had to be brought into the sphere in sections. The airlock doors were 7 feet wide by 9 feet high, and there was not much room to spare as the main beam of the crane was winched in. The 115 feet crossbeam was to be supported by 2 inverted U-frame girders, the legs of which would run on a circular rail track around the edge of the vault. Temporary derricks and winches were brought in to lift each complete beam of the crane into position. When in operation, it will be used for handling the charge-discharge machine and other items of heavy equipment. When the crane had been erected and the winches and lifting tackle had been removed, the airlock became a temporary changing room for the men working under the clean conditions which had been established for work on the reactor vessel. At this stage, a 4-foot thick shield of borated graphite was being built around the vessel. On the vault floor, the bricks for this shield were unpacked and lowered down a chute for positioning below the vessel. This shielding was necessary in order to slow down and capture fast neutrons escaping from the core. The thick concrete vault would provide a biological shield against gamma radiation from active materials inside the vault. Laying the graphite started in the confined space under the reactor vessel. Every brick was numbered and marked off on the plan before being laid. Spacing pieces were temporarily used when placing the bricks in each layer to ensure that they were the right distance apart. In the center of the surrounding wall was a region of pure graphite to enable measurements to be taken of the fission rate of the reactor when in operation. Vacuum cleaners were in frequent use to remove every trace of dust from the bricks during the laying. Shaped bricks were fitted around the 48 coolant pipes running from the vessel to the primary heat exchangers. As work progressed, the layers of bricks were carried up around the sides until the shield wall was level with the top of the vessel. Inside the vessel, the breeder housing had been installed. In the center of this would be placed the hexagonal core, 21 inches high, the heart of the reactor. Reaching out directly underneath the core are the bottom arms of the control mechanisms. There will be 12 of these, each with a cup at the end for the carrier frame of the group of control elements. From the outside, there was no indication of all the activity that was taking place inside. The outer rotating shield, slung in a lifting frame, was being installed. On the underside of the shield was a double cylindrical skirt which would fit into double channels set around the top of the inner wall of the vessel. These would be filled with a liquid metal to form a low-pressure gas seal during reactor shutdown. Around the top of the vessel, set in between the control rod housings, were the roller bearings on which the shield would rotate. The inner shield was then lowered into the hole, set eccentrically in the outer shield, and was supported by roller bearings set around the top. Similar skirts were fitted between the rotating shields to maintain the necessary seal. During the operation of the reactor, both shields will be raised off their rollers by jacking mechanisms and bolted up to flanges to form high-pressure gas seals. When the two shields were in position, the outer gear rings, driving mechanism and ancillary control equipment were fitted. Both shields could rotate independently of each other, and many weeks were spent in checking the 2,500 individual positions required for the charge and discharge of elements. The 2'9" plug was then lowered into the hole in the inner shield. Both the inner and outer shield plugs were filled with borated graphite and mild steel plates, and the purpose of the 2'9" plug, similarly filled, was to complete the shielding of the top of the reactor. In operation, This plug would normally only be removed to provide access for the possible withdrawal of the core skirt and tube vest from the reactor. By this time, the Goliath Crane was in commission. Fitted with two hoists, one of 25 tons and the other of 7.5 tons, it rotated on a single track set in the floor. The span of the crane extends beyond the vault floor so that either of the hoists can be used to move equipment from any part of the sphere. Controlled by one operator in a cabin under the main beam, the heaviest piece of equipment that the crane handles is the 25-ton charge-discharge machine. On the reactor, it could now be seen how the two rotating shields, the inner and outer, can scan the core and the breeder blanket for charging or discharging elements. The rotation of each shield is operated from a separate control column. It is powered by a motor driving a gear ring on the periphery of the shield itself. The outer shield is rotated. And as it turns, so the charge hole moves over the breeder blanket and core. As the shields rotate, the operators can line up on any particular element by observing through their periscopes graduated marks on the gear rings of the shields. These marks correspond to the element position. So, by rotating either or both of the shields, the charge hole can be lined up on any one of over 2,000 element holes. Surrounding the hexagonal core are the 12 triangular control sections which, seated on the ends of the horizontal arms of the control rods, can be moved up or down to control the reactor in operation. In November 1958, members of the Fast Reactor Design Office from Risley and the constructional engineers of the industrial group handed the reactor and plant over to the operating staff. The completion of this, Britain's first full-scale fast breeder reactor, is an outstanding example of the magnificent teamwork of the designers, planners and engineers, both civil and mechanical. No less an achievement was the work of the instrument and electrical engineers in designing and installing the incredibly complex instrumentation and power supply equipment. A few figures will give some idea of their task. In the control room alone, nearly 3 miles of multi-core cable was laid and required 3,000 junctions. For instrumentation in the sphere, 30 miles of cable was needed with 130 separate control panels. Months of commissioning followed before the reactor could be ready for operation. Designed and built by the industrial group of the Atomic Energy Authority, the Dounreay fast breeder reactor is in the main a full-scale experiment. The knowledge gained from its operation is planned to lead to the construction of this type of reactor on a full commercial scale.